All right, we're going to take a look at integration using trig substitution. And basically, this method of integration allows us to take some complicated integrals that involve square roots and rewrite them as trigonometric functions via a substitution process. And then when we finish integrating, we re-sub back in for the square roots to get back to the original. So it's a little bit in concept like U substitution, but it's dealing with using trig to substitute in for square roots. So this table just tells us effectively which substitution you need to use and when it's okay, and which identity you need to use. So this is really a reference table more than anything. Your job when you take a look at a problem like this first one says we're going to evaluate the integral of the square root of 9 minus x squared over x squared. So your job is to say, okay, here's my square root. It's 9 minus x squared, so it's in the formula of a squared minus x squared, where a happens to be 3. I'm going to go ahead and write that in. We have a equals 3 here. And the substitution we're going to use is x equals a sine theta. So x equals 3 sine theta. And then I'm going to do a couple things to do the substitution. Number one, I now can sub in for the square root of 9 minus x squared, plugging this in for x, but I also need to find an x squared and I need a dx to complete all of my substitutions. So dx I can just get by differentiating here. 3 sine theta differentiates to 3 cosine theta d theta. And then x squared I can get just by squaring both sides of this expression or this equation. So x squared equals 9 sine squared theta. So I have all of the substitutions I need to rewrite the integral. I'm going to rewrite it like this. The square root of 9 minus 9 sine squared theta, because remember I'm taking the x and I'm squaring it. This is my x right here, and I needed minus x squared. All divided by x squared, which was 9 sine squared theta. And then I have to sub in for dx, and my dx was 3 cosine theta d theta. And then I've got a lot of simplification to do. I could take the 9 out of the radical, and when I take the 9 out of the radical, it square roots to 3, and then underneath the radical, I'm going to be left with, if I bring out this 3 here, this will be a 1, and this will be a 1, so 1 minus sine squared theta. Going back to the chart, notice that when I have a radical in the form of a squared minus x squared, my identity that I use is going to be 1 minus sine squared theta equals cosine squared theta. So that gives me, instead of the square root of 1 minus sine squared theta, it's going to be the square root of cosine squared theta. And of course, that square root is just cosine theta. And then I have 9 sine squared theta still in my denominator. And then I'm multiplying by 3 cosine theta d theta, which I had subbed in for my dx. So when I clean this all up, my 3 times 3 over 9 go away, and I have cosine squared over sine squared, which you all should recognize as, cotangent squared. I was about to write in tangent squared, but cosine squared over sine squared is cotangent squared. So cotangent squared is probably not something that you've memorized as to how it integrates. But it does have a known integral, and that known integral is actually negative. Actually, you know what I'm going to do? I'm going to use another trig identity. I'm so sorry for getting a little scattered there, but cotangent squared I'm going to rewrite as cosecant squared theta minus 1 d theta. And then cosecant squared actually has the known integral. Cosecant squared integrates to negative cotangent theta. And then 1, of course, integrates to just theta. And then I have a plus c. But I'm not done with my substitution yet. And this squared was over here. It's bothering me. There we go. This is not my final answer because I have a theta here and a theta here, but my original integral started with an x in it. That's where this triangle comes into play. You've probably been wondering why this triangle is here. Well, I'm going to start with x equals 3 sine theta, and that means that sine theta equals x over 3. So if I take this triangle and I label this as theta, and I know that my sine theta is my opposite over my hypotenuse, I can use the Pythagorean theorem to solve for this side, which is going to be 9 minus x squared. That should look familiar. Boom, there it is. So in order to sub now in for the thetas, I have to use really anything from this triangle I could use to solve for theta, but I'm going to go with arc sine, because if sine theta is x over 3, then arc sine of x over 3 is my theta value. And so coming over here, what I'm going to do is I need to sign in for theta. I need to sub in for theta. So theta is going to be the arc sine of x over 3. And then cotangent theta, negative cotangent theta, I literally read off of the triangle. Cotangent is my x value over my y value. So the square root of 9 minus x squared over x. And this is my final answer. Now, just going to make a comment here. I kind of waved my hand at, first of all, knowing that cotangent squared is equal to cosecant squared minus 1. That is derived from the basic Pythagorean identity of sine squared plus cosine squared equals 1. And then I definitely waved my hand at cosecant squared integrates to negative cotangent. That's really very similar to, you know how secant squared integrates to tangent? Well, cosecant squared goes to negative cotangent. So it is related. It's not something that I really need you to memorize, but it does come into play in this particular problem. All right, let's go on to the next example, which is on the next page here. And here they're giving us 1 over x squared times the square root of x squared plus 4. So I need to recognize that this radical is in the form of x squared plus a squared, or a squared plus x squared, where my a value is going to be 2. And so I go to the second row of my chart on the prior page, and I get that my x value is 2 times tangent theta. And I'm going to go ahead and fill in the triangle, because if tangent theta is x over 2, that means opposite over adjacent is x over 2. And with the Pythagorean theorem, I get that this is the square root of 4 plus x squared, which in fact does match what's in here. That's always going to work with trig substitution. So let's just do some a little bit of work to get us to the point where we can sub in for everything. We know that x squared is going to be 4 tangent squared theta. And we know that dx is going to be 2 secant squared theta d theta. So when I do my substitutions, I have dx in the numerator, so 2 secant squared theta d theta. And then in my denominator, I have the square of x, which is 4 tangent squared theta, times the square root of x squared plus 4, and that's going to give me, let's see, x squared is 4 tangent squared theta, and then plus 4. So now I work all the simplification. First, I can pull out these 4s, make those 1s. That brings a 2 out in front, but in my denominator, that will cancel with this 2. And then I'm going to have in here, I've got tangent squared plus 1, which is in fact secant squared. And when I square root that, it'll just go to secant. So let me work on some rewriting this simplified. I have secant squared in my numerator, and in my denominator I'll have 4 times tangent squared, and then the square root of secant squared, which is secant. Then I'm going to be able to knock out this secant with one of those degrees of secant right there. And I need to figure out how to integrate secant over 4 times tangent squared. And the way that I would do this is kind of rewrite it all in terms of sine and cosine. And I won't go through all of the details, but I know that secant is 1 over cosine, and I know that tangent squared is sine squared over cosine squared. So I can manipulate this to have the 1/4 out in front, and it will get me to a cosine in the numerator divided by a sine squared in the denominator. And hopefully you can see at this point that you can use u substitution. And u substitution with this, I'll do a u equals sine and a du equals cosine. And so I'm integrating 1/4 times the integral of 1 over u squared du, which gets me to negative 1/4 u to the negative 1, which of course u was sine. So I have negative 1/4, and then instead of sine to the negative 1, I'll just use cosecant of theta, and I need a plus c. So that's all well and good, except now I have to sub back in for theta, and if you remember, theta is going to be, I could use, for example, if I did cosecant of theta, that's probably the easiest. Cosecant is going to be hypotenuse over opposite. So it gets me to, put it in black here, it gets me to negative square root of x squared plus 4 all over x, and that's plus c. So remember, I have cosecant, and that is hypotenuse over opposite.